Today's speaker is André de Gouvea. He is a professor at Northwestern University and well known for his expertise on the question of neutrino physics. André got his undergraduate in physics in Rio de Janeiro, Brazil, working at the Catholic University there, and also his master degree. Funny why his master degree was about an experiment at Fermion back in 1995. Then he came back to the States because I think he was born in the States. And then and did his PhD at Berkeley. He finished it in 1999, working with Hitoshi Murayama. And the thesis title, I want to emphasize it, was supersymmetric versions of the standard model. That's why I like André so much. Then after his PhD, he went for a postdoc at Sun, that I believe is where I met him. Then he stayed there for a few years before coming back to Fermilab. Then where he became a postdoc before joining the faculty at Northwestern. And he is at Northwestern since 2003. André is a fellow of the American Physical Society and the AAAS. And as I said, he's a renowned physicist working in the area of neutrino. So he's so good in giving talks that I think at some point he was overwhelmed because whenever somebody wanted somebody to talk about neutrino physics, so André was the invited person. So then, so probably he was giving 365 talks a year. So with that introduction, and I will let André to tell us about Majorana or Dirac neutrinos. That is the question. Thank you.
Okay, thank you. I hope you can hear me and you can see my slides fine. So speaking of giving talks, when I was invited to give this talk, I thought I had given a colloquium at Chicago in the not too distant past. That turned out to be false. It was about 10 years ago. So 10 years is, it's been long enough that all the young people are new and all the old people have forgotten what I said the last time. So I think I'll be safe. So what I want to try to do today is to tell you a little bit about neutrinos. This is meant to be a colloquium. So my job is to make sure that all of the experts on neutrino physics and particle physics will be bored, but hopefully everybody else will get a sense of some of the excitement that's going on in neutrino physics in the last many years. And I'll try to concentrate on the second half of the talk in this one of the big questions in neutrino physics, which is trying to distinguish or establish if the neutrino is a Majorana fermion or a Dirac fermion. And I'll spend some time trying to explain what that question means and why it's so hard to get an answer, and giving you a flavor of the types of things we can try to do in order to answer the question. Okay, so just to get started in the very beginning, for people that don't know anything about neutrinos, neutrinos are among the fundamental particles that we know about. So this plot here has a slide with the pictures of all the different fundamental particles. You must have seen lots and lots of versions of this plot. This is probably the most accurate one in case you're curious. And the neutrinos are among the fundamental particles in the standard model. And these are the particles that I want to talk about. If you're not in particle physics, you probably know that most of these particles are very rare, very short-lived, and they only exist in laboratories, and they're produced for a very short period of time. The neutrinos are not like that. The neutrinos are amongst the particles that we know about that are actually very relevant for the universe as we know today. The other particles that are on the same footing with the neutrino are the electron, which as far as we know is a stable particle, the photons, which are bosons, so they are destroyed and produced all of the time, but they pretty much exist everywhere in the universe, and then some combinations of the up and the down quark. So the neutrinos are on the same footing with these particles. And I'll try to give you a sense of this feature of neutrinos by telling you things that everybody should know. But if you don't know, at least you have something to impress your friends. So, like I said, neutrinos are not particles that go away. And they're also not particles that are rare. Neutrinos are incredibly abundant. One thing that almost everybody knows, if you've been around long enough in physics, is that neutrinos are produced in very, very large numbers in the sun. So the sun is a gigantic neutrino factory. It's also a photon factory that we know very well, but it also produces a lot of neutrinos. And the number that everybody seems to remember is that if you look at an area the size of your thumb, you get about 100 billion neutrinos from the sun traversing that area every second. So neutrinos are not just some rare particle that's never produced anywhere in the universe. Even if the sun was not around, we would be able to produce neutrinos here on Earth without relying on the stars. For example, cosmic rays bombard the atmosphere all of the time. That produces particles that we call pions. The pions decay and they produce neutrinos. Neutrinos are also copiously produced in radiative decay processes. So a nuclear power plant is a place where we end up producing a lot of beta decaying nuclei. And these beta decaying nuclei turn out to decay and produce a lot of neutrinos. If you don't like nuclear power plants, neutrinos come out of radioactive processes in general. Apparently, the fruit of choice for talking about neutrinos is a banana. I think the reason is that bananas have a high potassium content. If you don't like bananas, the same goes for coconuts. And again, if you take your typical banana, that banana will produce about 1 million neutrinos every day. If you're scared of bananas, you might want to be reminded of the fact that people have a lot of potassium in them as well. So we're also producing neutrinos all the time. And actually, you shouldn't really care about the neutrinos. You should care about the fact that people are kind of radioactive. So you should remember that when you go to bed with your spouse tonight. And of course, neutrinos are also produced elsewhere in the universe. One thing that's very well known about neutrinos is that they're copiously produced in supernova explosions. So this is a picture of the explosion of a supernova. This is an after and before picture. I'm not responsible for displaying it in this weird order. But the supernova explosion is this very, very bright object that you can see. And the before picture is where the arrow is pointing. And what we like to say is that if we could measure the amount of energy that's emitted in neutrinos, as well as we can measure the amount of energy that's emitted in the optical range, the amount of energy emitted in neutrinos is about 100 times bigger. So basically, a supernova explosion is a neutrino event where a little bit of light is also produced as a side effect. And finally, of course, neutrinos are relics of the Big Bang. So we've all heard the story about the Big Bang, and it turns out that as the universe was created, a whole bunch of neutrinos were also created, and these neutrinos stick around. And a very impressive number to keep in mind is that if you had eyes of particle physics today and you were looking at, or you were doing an inventory of the universe, the most abundant particle in the universe by far is photons. So, so if you want to describe the universe in very gross features, the universe is a thermal bath of photons. That's it. That's the universe. The second most abundant particle are neutrinos. They're almost as abundant as the photons. That's what's depicted here in this plot on the right-hand side. Next, after neutrinos, as far as we know, there are protons and electrons and neutrons. But the proton to photon ratio is about 1 per billion or 10 billion. So everything that makes up ordinary matter that we know about is a very, very tiny fraction of the number of photons that are out there in the universe, and also the number of neutrinos that are out there in the universe. There's this thing called the dark matter, and we have no idea what it is. So we have no idea how much there is of it. We only know how much it contributes to the energy budget of the universe. So again, neutrinos are everywhere. So they're not just one of these exotic, weird particles. They're actually a big player in the history of the universe. And of course, I should pause here and just let you know that it took us a very long time to understand that these particles were here. And the reason is, of course, that even though they're here and they're everywhere and they're being produced in gigantic numbers in stars and beta decay and so on, they are ridiculously hard to detect. So that's why, as you were growing up and before you knew anything about particle physics, you never knew about neutrinos because they're just here, but not really because we can't detect them. The reason for that is that they only interact via the weak force. And it turns out that the weak force is very weak. There are a couple of impressive numbers that you can keep in mind. One is, I told you that the sun produces neutrinos. If you're very worried about that, and you wanted to shield the universe from this neutrinos produced in our sun, you could do that. You could construct a wall of lead, a spherical wall of lead around the sun. And if you wanted to do that very efficiently, the wall of lead should probably have about the thickness of the solar system. So if you did that, then you could shield all of the neutrinos from the sun. A different number to have in mind, which I think is more useful, is you can ask yourself, so you're being bombarded by these neutrinos from the sun all the time. So you can ask, what's the likelihood that one of these neutrinos will actually hit you? And the answer is, it'll probably happen for you once in your lifetime. So you should be on the lookout. One of these days, one of these neutrinos is going to hit you, and you're allowed to make a wish. And then you see what happens after that. But that's about the rate. So the rate of you being hit by a neutrino is once in your lifetime if you're lucky. And of course, that's a very challenging experimental problem to actually detect neutrinos at all. And we got around this by learning how to build ridiculously big detectors. But that's not what I want to talk about. What I want to talk about is to start discussing a little bit more of the physics. And it turns out that if I was giving this talk 25 years ago, it would have been a shorter talk because I would be able to tell you that it turns out that there are 3 neutrinos. We would describe them by their flavor. And the flavor has to do with the fact that the neutrinos have weak interactions. They talk to the W boson and the Z boson. The W boson interacts with neutrinos and the charged lepton. The charged leptons are the electron, the muon, which is a heavier version of the electron, and the tau lepton, which is a heavier version of the muon and the electron. And it turns out that every time a W boson interacts in a way that involves an electron, it produces a neutrino. And every time the W boson interacts in a way that involves the muon, it produces a different neutrino. And every time the W boson interacts in a way that involves the tau lepton, it produces a third kind of neutrino. And we've been able to identify the fact that these neutrinos are different. And the way that we do that is when we take the neutrino that's produced together with the electron and we make it hit something and produce a charged lepton, that charged lepton is always the electron. When the neutrino that's produced together with the muon hits something, it produces a muon. And when the neutrino that's produced together with the tau hits something, if you're lucky, it produces a tau lepton. And in that way, we can distinguish them. Again, in the last century, we thought that the neutrino masses were 0. And that made the neutrinos special because not only we thought that their masses were 0, we also could get away with describing only a small number of neutrinos degrees of freedom. And what I mean by that has to do with spin. And I'll talk a lot more about this as the talk goes on. But basically, the 2 neutrino states that we know about is a left-handed one. And that's the state that we normally call the neutrino. And we also know about a right-handed one, which is a state that we normally call the antineutrino. And I'll have a lot more to say about that in a little bit. Okay, so the reason neutrinos have gotten super duper popular these days is that it turns out that this story that I just told you was not completely correct. So if we go back to this picture, it turns out that if you have a neutrino that's produced together with an electron, it doesn't always hit something and produce an electron. Sometimes it can hit something and behave like a different flavor. I didn't say this explicitly, but the objects that we have here are called the electron neutrino, the muon neutrino, and the tau neutrino. So what we learned is it's possible to produce a muon neutrino and have it behave like a tau neutrino, or to have an electron neutrino being produced, but have it behave by, let's say, a muon neutrino, and so on and so forth. And in order for you to get this to happen, you just have to wait. So what this means is, if you produce a muon neutrino and you wait long enough, it will have a non-zero probability of behaving as a different kind of neutrino. If you don't wait long enough, this doesn't happen. But if you do wait long enough, then you can get this flavor changing phenomenon. This is important because it's telling us that neutrinos have a sense of time. That means that they know when a short amount of time has elapsed or when a long amount of time has elapsed. The final conclusion to this saga, which is still ongoing, which is to understand how neutrinos change flavor and how much this flavor changes as a function of the distance that they traverse, I think the final result of the story, which is the thing that I want to concentrate on, is that you can only explain these phenomena by postulating that neutrino masses are not zero. And again, if you just want a bird's eye view of what's going on, the hint that neutrinos must have a mass comes from the fact that the neutrinos have an internal clock. They know a short amount of time from a long amount of time. And it turns out that only massive particles know how to tell time. Massless particles live in a very strange universe where everything happens in quotes at the same time. Again, this is not what I want to talk about, but I do want to advertise that basically what we learned is that the electron neutrino, the muon neutrino, and the tau neutrino are not really particles. They're just interaction states. The real particles, we like to call them nu1, nu2, and nu3, which are really boring names, but they've stuck, so we're stuck with them. And it turns out that the nu1, when it talks to a W boson, it can either interact with the electron or the muon or the tau, and it has different probabilities for interacting with the different charged leptons. So again, you have these three different states. They can all talk to the electron and the muon and the tau, and that's the correct way of understanding neutrinos today. And this is not what I want to talk about. What I want to talk about is to give you a sense of why theorists care about these discoveries. And the discoveries are easy to describe in words. So the first way that I want you to look at this is to stare at the plot on the left-hand side. This is a plot of all of the fermion masses in the Standard Model in the same plot. And I don't want to spend too much time talking about this, but just to impress upon people, especially people that are not in particle physics, how ridiculous this plot is. And the reason it's outlandish is the fact that all of these points here in this plot are the masses of fundamental particles. And the masses of these fundamental particles can differ by, 10 orders of magnitude, which is sort of outlandish, but it's true. And again, we go all the way from, say, the top quark mass, which is bigger than 100 GeV, so it's more than 100 times heavier than the proton, all the way down to the neutrino masses that we actually don't know. We only know that some of them are not zero, but we know that for sure they're way below 1 electron volt. And then the masses of all of the other particles fall in between the neutrino and the top quark. The thing which I do want to impress upon people is the fact that if you stare at this plot with this log scale y-axis, you should be able to figure out that the neutrino masses are super small compared with anybody else's mass. So they don't seem to fit very well. So when we say that neutrino masses are weird, they're weird because they don't seem to fit in the picture of masses that we know about. The other feature about neutrinos, which I don't want to talk about, but I want to mention, is the fact that we've measured what's called a lepton mixing. And a lot of people spend their time understanding why lepton mixing looks the way it does. And I think the discovery that we have made is the fact that lepton mixing is very different from quark mixing. And that seems to get people excited. But I don't want to talk about that. I do want to talk about the neutrino masses. And the reason they're very exciting is the fact that they're telling us something that's fundamentally important. I want to try to give you a cartoon of why this is important and what we think neutrino masses mean to us. The idea is the following. So let me go back to this pretty picture here. And of course, this is not just a picture. It's a mnemonic device that allows us to remember the mathematical structure of what we call the Standard Model of particle physics. And it's a great model. It turns out it's the result of a lot of research in particle physics, both theoretically and experimentally. And it is described in terms of what's called the relativistic quantum field theory. And it turns out that in order for these theories to be self-consistent and predictive, they're very constrained. And the end result of that is the following. If you decide that you want to write down a theory, which is a relativistic quantum field theory, you just have to specify a few things. And the few things you have to specify are, what are the objects in your theory? They're fields. And then you also need to specify which rules these fields have to obey. Once you've done that, writing down the theory becomes sort of trivial. So once you know what the players are, and once you know what the rules are, you can write down all of the possible interactions and you're done. You can just calculate away and you can make a bunch of predictions. And you don't have a lot of wiggle room. The reason I'm mentioning this is that if you take the ingredients that we know about and the rules that we know about, and you write down the Lagrangian for nature according to our model, you actually make a prediction. And the prediction is that neutrino masses are exactly zero. It's a great prediction. It can be tested experimentally, and it's wrong. So that's why people are excited. It's because we made a prediction in our great model, and the prediction is incorrect. So what does that mean? It doesn't mean that the whole theory that we wrote down is wrong. We think it means that there's some ingredient missing. So there's something missing in our standard model that prevents neutrinos from getting a mass. And that's why theorists are so excited, because we like to learn that our model's wrong so that we can try to fix it and hopefully end up with a better model. And of course, we're very good at inventing solutions that explain why neutrino masses are not zero. And of course, we tend to be too good, so we tend to invent too many solutions. Let me say this again very quickly, but not too quickly. The reason people are excited about neutrino masses is the fact that they imply the existence of new fundamental fields. So in our lingo, there are new particles that we don't know about. That's what we've learned. Sadly, we don't know very much about what these new particles should be. We don't know if they're more fermions. We don't know if they're new bosons. We don't know if they're very light particles. We don't know if they're very heavy particles. We don't know if they're charged or neutral. And we don't know if we can find them in experiments. But we know they exist. So that's progress. And I do want to point out that in particle physics, there aren't too many things that our model doesn't explain. Actually, the number of things is very small. So that's what's in this footnote here. So everything that we're very sure that we don't know fits in this footnote. And it revolves around things like the dark matter. We're pretty sure dark matter exists. We're pretty sure it's not made out of standard model particles. There's another funny question we like to ask, which is, I told you that the ratio of protons to photons is about 1 to 10 billion. That number turns out to be too big. Given everything that we know about particle physics, that number should be like 1 in 10 to the 18. So the question is, how come there are all these protons around? And we think the answer lies on fundamental particle physics, but it's not something that the standard model can explain. It's the issue of what's called baryogenesis. Finally, there's another feature of the universe we don't understand, which is when we measure the expansion rate of the universe, it seems to be accelerating. We don't know what kind of a physics leads to this. And some people believe this is a particle physics problem, but we have no idea what the answer is. That's the dark energy problem, which I know absolutely nothing about. But neutrinos then are amongst these questions. They are amongst the things that we're very, very sure are there, and they're features of nature that our model of particle physics cannot address. So that's why neutrino masses are so exciting. Now, for the particle physics people, I want to give you a slide that tries to explain what's exciting about giving neutrinos a mass. And the way to think about this is the following. First of all, as people who are in the particle physics business know, masses are annoying. So particle masses are hard to come by in particle physics. And this is a complicated story, but basically all particle masses come from something called the Higgs mechanism. So neutrino masses are not different in that way. Neutrino masses also come from electroweak symmetry breaking. So some manifestation of the Higgs mechanism. Now, what makes neutrinos exciting is that you have choices. And the choices are more diverse than the kinds of choices you can make for the charged fermions. And again, here there's a list of possible choices that explain how neutrino masses come about. And one possibility is that neutrinos get a mass just like everybody else, which is still a possibility, and we may have to live with that. Another very different possibility is that maybe neutrinos get a mass because they speak to a different Higgs boson other than the Higgs boson that they've discovered at the Large Hadron Collider. Another possibility is that neutrino masses are the combination of the Higgs mechanism, which gives you a source of mass, if you want to think about it that way, with a completely different source of mass. And this is a more complicated idea, which of course is also the idea that everybody likes. And again, you know, if you're a particle theorist, you get super excited about this possibility because it's telling you that neutrino masses are evidence of a new mass scale of nature that we haven't gotten to see before. And somehow, if you wanted to hyper summarize what particle physics is about, you know, we're about discovering the mass scales of nature where something exciting happens. And again, one mass scale where something exciting happens is what's called the electroweak symmetry breaking scale. It's the scale that the LHC is exploring right now. And it's the scale where something interesting happens and the masses of all the particles that we know about are directly related to what's going on around the Higgs boson. So what makes neutrinos exciting is that they might be our first hint that there's another mass scale in physics, which has nothing to do with the Higgs boson, but it's leaking information towards us through the non-zero neutrino masses. Now, my goal in this slide is just to tell you that there are very, very different ideas that explain how neutrino masses are not zero. They all require new degrees of freedom. And then the next question is, how do you tell these different ideas apart? And the answer is experiment. So we need more experimental data that will guide us towards figuring out which one of these different ideas that we have happen to be correct. And again, here's a long list of different types of particle physics experiments that might teach us about where neutrino masses are coming from. This is a very, very long list. It involves almost all different types of activities going on in particle physics. So they involve more neutrino mixing experiments, precision measurements of charged lepton properties, collider experiments, precision measurements of cosmology, lots of different things. And I want to talk about the first bullet there, which is appreciating the fact that the neutrinos are special and massive neutrinos are potentially very special. And that's the business of whether the neutrinos are Dirac or Majorana fermions. So this is what I want to do for the remainder of the talk, which according to my clock is about 20-something minutes. Okay, so that's my goal here. But again, you know, the idea is there's a very big picture of, we know there's something exciting going on. We don't know what the answer is. And we think the answer can come from lots of different places in a particle physics world. So again, what I want to talk about is answering the question or asking the question as to whether the neutrinos are Majorana fermions or whether they're Dirac fermions. And right away, I want to tell you that we have a program dedicated to trying to answer this question, which turns out to live in the world of nuclear physics, which is looking for a very rare process that we don't know if it happens or not, which is called Neutrinoless double beta decay. So what I want to do is not to talk about Neutrinoless double beta decay very much, but I want to try to explain in words to people that are not experts in particle physics what the question is about, why answering the question is difficult, what Neutrinoless double beta decay does, and what would be other ways of answering this question. And so that's kind of what I want to talk about. And it's an interesting topic that I happen to be thinking about today, and that's why I'm talking about this. Okay, so basically, the question that I want to ask, and the question of Dirac versus Majorana, has to do with asking how many degrees of freedom does it take to describe a neutrino? And it turns out, surprisingly, that there are two possible answers. One answer is 4, and the other answer is 2. And when it comes to the neutrinos, we don't know if it takes 4 degrees of freedom to describe a neutrino or 2 degrees of freedom. And I want to talk about this very slowly. And the way that I want to talk about this is to first talk about our favorite particle, which is the electron. It's our favorite particle because it's the one that we learn about the earliest. It's also the one that we witness very frequently in our daily lives, perhaps more in the winter when you get electric shocks and things like that. But it's the particle that everybody's very familiar with. And what I want to do is to do a Gedanken experiment, just to give you a sense of how particle physicists, at least theorists, like to organize things, because that turns out to be a useful way of thinking about neutrinos. So let's talk about the electron. And let's say we've never seen an electron before, but we start doing experiments, and we discover a particle that has negative charge, and we also identify the fact that it has spin, but more importantly than that, we identify an electron that happens to be left-handed in helicity. Now, helicity is just a sophisticated way of saying that we've measured the third component of the spin of the electron in the direction of the momentum. And again, I want to remind you of the fact that the electron has spin 1/2. And we know that the spin 1/2 describes 2 different states, which we can call them like the spin up and the spin down. And of course, up and down are completely arbitrary because they depend on your definition of up and down. And when you have a particle that has momentum, we can define positive helicity when the particle has spin up in the direction of the momentum, and negative helicity when the particle has spin down relative to the momentum. If you don't like up and down, we normally like to call them left-handed and right-handed. And the right-handed is like up, and the left-handed is like down. So again, imagine you're doing an experiment and you discover a left-handed electron. What's interesting is once you've discovered that a left-handed electron particle exists, you can make a prediction. And the prediction is if the left-handed electron particle exists, there's another particle which is right-handed and has the opposite charge, which we call the right-handed positron. So the left-handed electron and the right-handed positron must exist if our understanding of particle physics and field theory is correct. Okay, so again, you made one measurement and you've discovered 2 states, which is good. If you keep working on this electron particle that you've discovered, you will eventually discover that the electron has mass. So if you discover that the electron has mass, you can also learn another thing for free, which is that if a left-handed electron exists, a right-handed electron also exists. The reason for this is simple. So if the particle has mass, you can go to the electron rest frame. And if I tell you that a left-handed electron exists, it's kind of like telling you that you've detected an electron would spin down. And without doing any new measurements, you can conclude that there has to be another state, which is an electron would spin up. Imagine a world where only electrons would spin down existed. It wouldn't make any sense. And it has to do with Lorentz invariance or rotational invariance. And the silly explanation for why you can't be in a world where all the electrons have spin down is because you can kind of flip upside down and then they all look like they have spin up. And you can't be in a world where up and down are different. So if you bought that, then that's good. So again, if the electron has a mass, there's a left-handed electron, a right-handed electron. And again, by the CPT theorem, you must also have a right-handed positron and a left-handed positron. So long story short, the electron is described by 4 degrees of freedom. The electron would spin up and down, and the positron would spin up and down. And these four states are something that we refer to as a Dirac fermion field. So it's a Dirac particle. Okay. Now, I do want to add a quick aside, which is in this story relied on the CPT theorem, which is a big theorem that we don't want to violate. So it's always true, and you can't question it. And it's also relied upon the fact that the electron has mass. If the electron didn't have a mass, we could have gotten away with there being only a left-handed electron and a right-handed positron, or a right-handed electron and a left-handed positron. You don't have to have those two particles exist at the same time. This sounds very weird, but it's completely consistent for a massless particle, because a massless particle can't stop. So you can't go to that particle's rest frame. And it turns out that if the particle is left-handed in some reference frame, you can go into any reference frame that you like, and the handedness of the particle is always the same. So you could be in a world where all of your electrons were left-handed, as long as the electron mass were not zero. This is the world that we were before we discovered that neutrino masses were not zero. And I think that's one of the important things to appreciate about neutrinos. Okay, let's talk about neutrinos. And we can tell the same story. So we've discovered left-handed neutrinos. They have a partner called the right-handed antineutrino. That's what we normally call that. And again, for a very long time, before we knew neutrino masses were not zero, we were very happy to live in a world where these are all of the particles that existed. Now we've discovered that neutrinos have mass. If we go back to the electron question, if we can see a neutrino with spin up, there has to be a neutrino with spin down, and the same goes for the antineutrino. So that's what the neutrino mass story is telling you. What makes the neutrino special is that it turns out that when you say that there's a neutrino with spin up and there must be a neutrino with spin down, you actually have a weird choice, which is the following. The left-handed neutrino already has a right-handed partner because of the CPT theorem. So when it comes to talking about the Lorentz partner of the left-handed neutrino, the up and down, you have a choice as to whether you want to make the Lorentz, so this particle here, which is related to the left-handed neutrino, it could actually be the same as that particle there. So the picture, a nicer looking picture is this one here at the bottom. Or it could be a different particle. So you have these two qualitatively different choices to make. And the key point is, if you make the choice on the bottom, you only have a left-handed helicity state and a right-handed helicity state, and that's it. So only 2 degrees of freedom. Or you have a left-handed helicity particle, a right-handed helicity particle, a right-handed helicity antiparticle, and a left-handed helicity antiparticle. So in the top case, the neutrino kind of looks like the electron. In the other case, it doesn't. It has fewer degrees of freedom. Now, this is kind of overkill, but it's important to appreciate the fact that with the electron, you didn't have this choice. And again, the question you're making is, can this particle here, the right-handed positron, be the same as the right-handed electron? And the answer is instantaneously no. And we know that for sure because they have different charge. One has plus charge, one has minus charge. You would never get them confused. Because the neutrinos don't have charge, you have this extra choice. Okay, so again, the question that we're asking is, are there 4 neutrinos, are there 4 degrees of freedom in the neutrino, or are there only 2? And the point I want to make, and again, I'm talking about this very slowly, hopefully it's useful for people, is the fact that we don't know what the answer is. And again, if you've never heard about this before, you should be surprised, because again, 4 and 2 are very different numbers. So how do we get them confused? And the reason is that if the neutrino mass was 0, this would not be a physics question. Again, if the neutrino mass is 0, your experiments can speak to these two particles here. And it turns out, and I'll give you some examples of that, there's no experiment you can do if the neutrino mass is 0 to ask if these other states exist or not. So if you have some states that don't couple to anybody and don't do anything, you're not really allowed to ask if they exist or not. It becomes a non-physics question. So the only connection to the potential existence of these extra degrees of freedom is the neutrino mass. And if the neutrino mass were 0, you would not be able to ever access these states. Let me say this in a different way, which hopefully is useful for people. So basically what I'm trying to say is, if the neutrino mass were 0, you can't ask if it's a Majorana fermion or a Dirac fermion. It's not a physics question. This explains why we don't know the answer yet, because the neutrino mass turns out to be very small. So even though the neutrino mass is not 0, for all practical purposes, most of the time it behaves as if it were 0. And again, if it were exactly 0, you wouldn't be able to ask the question. So that means that in the limit where the neutrino mass is 0, you can't get an answer. And again, just to summarize the thought, if you can't ask a question, you can't get the answer to the question. What this means in practice is, if you can construct an observable that can answer the question for you, that observable better be trivial in the limit where the neutrino mass is 0. And that's the end of the story, which is, if you can construct an observable that knows if the neutrino has 4 degrees of freedom or 2 degrees of freedom, that observable is going to vanish proportional to the neutrino mass. So the amplitude for that physics process is proportional to the neutrino mass in some units, which is usually the typical energies of your experiment. And it turns out that because neutrino masses are so small, it becomes very difficult to get an answer to the question. So I want to say a little bit more about this because I think it's a funny feature of the standard model that makes answering this question very difficult. And it has to do with the weak interactions. And I'll talk about this relatively briefly, just to give people a sense of things that we've known about the weak interactions for a long time, but they're kind of weird. And it's not special to neutrinos. So for example, we know about the muon. The muon decays into electrons in some neutrinos. And it turns out that independent of the state of the muon, when the muon decays, the electrons that come out are heavily polarized. They tend to be mostly left-handed, with a tiny probability of being right-handed. When the mu plus decay, by the way, the positrons that come out are almost 100% polarized in a right-handed way. This is weird, but it's a feature of the weak interactions. The weak interactions are left-handed, not because of helicity, but they have a property called chirality, which is of the left-handed type. And it leads to this thing called parity violation, which is that when the muon decay, it really likes to produce electrons that are heavily polarized and positrons that are heavily polarized. The story is actually more dramatic. If the electron mass were 0, the electrons would be 100% polarized in the left-handed state, and the positrons would also be polarized in the 100% in the right-handed state. And again, this has nothing to do with neutrinos. It's a property of the weak interactions. So when we produce a neutrino, for example, in pion decay, whenever we have a pi plus decay, the neutrino that gets produced is 100% left-handed, with a very tiny probability of being right-handed. And the probability is proportional to the neutrino mass. When the pi minus decays, and it produces some object that we normally call the antineutrino, but that object that gets produced is also 100% polarized. So again, the buildup of this is to say, when a pi plus decays, you get a left-handed neutrino. When the pi minus decays, you get a neutrino state that's right-handed. Now, when you detect a neutrino, you also have to use the same interaction, this left-handed chiral weak interactions. And when a left-handed neutrino state interacts and it produces a charged lepton, the nature of the interaction only knows how to produce charged leptons of a certain sign. So when a left-handed neutrino interacts, it only knows how to produce electrons. When the CP conjugate of that interacts, it only knows how to produce positrons. So the end of the story, or the summary of the story is, forget about calling neutrinos and antineutrinos. You can call them whatever you want, but it turns out that when a pi plus decays, the thing that comes out is a left-handed lepton object. And when the left-handed lepton object interacts, it only produces electrons. When the pi minus decays, it produces a right-handed object. And when this right-handed object interacts, it only knows how to produce positrons. This does not matter if the neutrino is Majorana or Dirac. So regardless of what the neutrino is, this is always what happens. The violation of that comes in these are very, very rare species that are produced with a very, very tiny probability. And just to give you a sense of scale, when the pi plus decays, you do have a non-zero probability of producing a right-handed Helicity neutrino object. But the probability for that to happen is something like 10 to the minus 20. So it's kind of rare. But that's what we're living with. That's the way that we can tell neutrinos are Majorana or Dirac. So a consequence of this story that I just told you is there's a symmetry associated to the massless or the zero mass neutrino case, and that's called the lepton-number. So it turns out if the neutrino masses were 0, you can assign lepton-number to the electron mu1 and tau and the neutrino as 1. And then the CP conjugate of the neutrino, which is the right-handed object, that would have lepton-number -1 along with the positron mu1 and tau. And every time you do an experiment, the total lepton-number is a conserved charge. And the reason we like to talk about this is because we're assigning a different quantum number to the neutrino and its CP conjugate. And it turns out that if the particle is a Majorana fermion, we shouldn't be allowed to do that. Because again, a Majorana fermion is of this type. And it basically means that, so if you look at the electron, this object and that object have equal and opposite charges. They don't have a choice. All the charges have to be equal and opposite. So if you assign a charge to the left-handed neutrino, the CP conjugate of that has to have the opposite charge, which means that this Majorana option is not allowed. Okay, so that's the end of that story. So I hope that wasn't too confusing. So let me give you an example of how this works in an experiment that can tell if the neutrinos are Majorana or Dirac. So again, let's say we have a physics process where an electron hits something and it produces a neutrino. Now, like I've been saying, the neutrino that you produce is almost always a left-handed object with a tiny probability of being a right-handed object. Imagine now that this neutrino is going to scatter against something. And like I said, when the left-handed object hits something, it only knows how to produce electrons with negative charge. It doesn't know how to produce electrons with a positive charge. However, this other component here, which is right-handed, actually has two different choices. One choice is if the neutrino is a Dirac fermion, this right-handed component doesn't know how to do anything. It doesn't interact. So it does nothing. So you do your experiment and nothing exciting happens if the neutrino chooses to behave in this way. On the other hand, if the neutrino is a Majorana fermion, this right-handed object here is the object that shows up in this type of interaction. And it's the object that knows how to produce a positively charged object, positively charged leptons. So that means that it is possible to have an electron come in, produce a neutrino, have the neutrino hit something, and if it behaves in this way, it actually knows how to produce a positron. And this is a process where the total lepton number changed by 2 units. You started off with 1 electron, and you end up with a positron. And that would be a hint that the neutrino is a Majorana fermion. The probability for that to happen is this number m over e squared. And if you plug in your favorite values for m over e, you get some ridiculously small number like 10 to the minus 18 or 10 to the minus 20. So needless to say, these are very difficult experiments to do. The way that we try to circumvent that is to take advantage of nuclear physics. So what we want to do is a nuclear physics experiment where a nucleus decays into another nucleus by emitting 2 electrons. So this is a physics process that preserves angular momentum, it conserves charge, it conserves everything except for lepton number. The nucleus in the beginning has 0 lepton number. At the end of the day, you have 2 electrons, so that gives you 2 units of lepton number. This violates lepton number. And the way that this looks when it comes to neutrinos is this is a process where you can have a W boson. And remember, the W boson goes into an electron and an electron antineutrino. The other W boson also goes into an electron and an electron antineutrino. But if the neutrino is its own antiparticle, those 2 antineutrinos can annihilate into nothing, giving you this physics process here. So that would only happen if the neutrino were a Majorana fermion. And we are in the business of measuring or placing a constraint on these types of decays as precisely as possible. And what's exciting is we can predict what the rate for this neutrinoless double beta decay process is supposed to be as a function of the neutrino mass. And we're getting into a point where life is getting to be exciting. And I don't want to spend time talking about this. For the last 5 minutes, which I think I may have, I want to talk about something completely different just for fun. And I just want to remind you that neutrinoless double beta decay does not have a monopoly on looking for lepton number violation. If you look at the particle data book, these are all the different ways in which you can look for lepton number violation. And you can see that they're all different types of physics here. Actually, I lied. There's a second page, which includes these other decays here. But neutrinoless double beta decay is the best way we have, or the most sensitive way we have, of looking for lepton number violation. What I want to talk about is something different, which is just for fun, and again, just for a couple of minutes, which is to go back to why is it so difficult to make these measurements? And it's really difficult to make these measurements because neutrino masses are very small. Now, of course, when somebody tells you that neutrino masses are very small, that's a meaningless statement because you have to say very small compared to what? And it's actually very small compared with the typical energy scales in your physics problem. So it's a technical problem. It's not a fundamental physics problem. So the question is, if you want to solve this problem as to whether the neutrino is Majorana or Dirac, you kind of have 2 different ways of doing it. One is you have to find something that only Majorana fermions know how to do and Dirac fermions don't know how to do. And the answer is Majorana fermions know how to violate lepton number. So you can look for the violation of lepton number. A very different route is that if you were working with neutrinos that are not so energetic, life would be way better. Because again, the reason you can't answer the question is that neutrino masses are very small relative to the energy scales in your problem. So what we really should be thinking about is, how do we work with neutrinos that don't have a lot of energy? So that's what I want to say just a few words about. Now, if you've never thought about this before, you should be asking yourself, so why don't we just do that? You know, why do we insist on working with neutrinos that have so much energy compared to their mass? The answer is the weak interactions, and that the neutrino masses tend to be small enough that it's hard to come by very low energy neutrinos. And if you did have very low energy neutrinos, the problem is the weak interactions cross sections become smaller and smaller as the neutrino energy gets smaller and smaller. So that means that the probability of detecting a neutrino becomes smaller and smaller as the energy becomes smaller and smaller. So that means that if you want to ask if the neutrino is Majorana or Dirac, on the one hand, it becomes easy to address if the neutrino is Majorana or Dirac in your experiment, except that your experiment has no rate. So you kind of have to choose. Do you want to be in a situation where you have lots of events, but it's very difficult to tell if the neutrino is Majorana or Dirac? Or if you want to be in a situation where you have 0 events, but it's very easy to tell if the neutrino is Majorana or Dirac. And of course, life is harder than that. And again, there are some opportunities, in quotes, for running into neutrinos that are not relativistic. And I think I'll discuss one example, which is an interesting example of neutrinos that I've already talked about, which is something called the cosmic neutrino background. And then maybe I'll say something about very low energy processes. So again, you know, the enterprise that we have is we want to find neutrinos that are not relativistic. They're actually easy to find. I mean, they're easy to catalog. And these are the neutrinos from the Big Bang. The Big Bang produced all of these neutrinos. And given everything that we know about neutrinos today, most of them are super cold today. They're not moving very fast. They are exactly what we're looking for. So let's talk about this cosmic neutrino background. So again, there's a cosmic neutrino background. Given everything that we know today, they're super cold. So that's good. That means that they're not moving fast. That means that they're not relativistic. And I want to convince you that distinguishing between Majorana and Dirac neutrinos is very easy. So the way I'm going to do that is I'm going to be measuring them via a charge current process. So my neutrino is going to hit a nucleus and produce an electron. And the point is, if this is the physics process that you're going to be looking for your neutrinos from the cosmic neutrino background, it turns out that it's twice as easy to detect these neutrinos if they're Majorana fermions. So it's a big difference between Majorana and Dirac fermions. This is relatively easy to understand, and I explained this here in words. So you have a neutrino at rest, and let's say that it was produced as the thing that we normally call a neutrino. It was a left-handed state when it was produced. It's very, very cold, and now you want to hit it. And you want to hit it using this interaction here. If you hit a neutrino that's sitting at rest with a chiral interaction, when you hit the neutrino, it will either couple to the left chiral field or the right chiral field. If the neutrino is a Dirac fermion, the left chiral field knows how to produce an electron. Good, so we get an electron when the neutrino behaves like a left chiral field. If it chooses to behave like the right chiral field, you're out of luck because the right chiral field doesn't know how to do anything, so it doesn't give you a hit. Now, you also have the antineutrinos in your cosmic neutrino background. And the antineutrinos, if the neutrinos are Dirac fermions, they're kind of hopeless because they don't know how to produce electrons. They only know how to produce positrons. So that means that you basically get a hit from the left chiral component of the neutrinos in the cosmic neutrino background. If the neutrinos are Majorana fermion, your cosmic neutrino background was born as a whole bunch of left-handed states and a whole bunch of right-handed states. All of these states are very, very cold. So when you try to speak to the left, to the thing that was born as a left helicity state, and you want to have this reaction here happen, if it behaves like a left chiral field, you get an electron. If it behaves like a right chiral field, the reaction doesn't go. The difference is, for the states that were born like a right helicity state, which we normally call the antineutrino, when you speak to that state and the neutrinos are Majorana fermion, that state is happy to produce an electron. Again, usually this is super rare because the probability for that to happen is proportional to the neutrino mass divided by the energy. But because my neutrino has effectively no kinetic energy, both the neutrino and the, in quotes, antineutrino are very, very happy to produce electrons for you. And that gives you a factor of 2 difference. That means that when you measure the cosmic neutrino background, if the neutrinos are Dirac fermions, you get answer 1. And if the neutrinos are Majorana fermions, you get answer 2. So this is super exciting. And then if you've never thought about this in your life, you're saying, How come I've never heard about this? The answer is that there's some challenges. And of course, the obvious challenge is we've never seen this cosmic neutrino background. We have never been able to do an experiment that is sensitive enough to see any of these neutrinos from the cosmic neutrino background. So that means we have a huge signal in an experiment that has 0 rate, which is unfortunate. There's another technical thing which I'll just mention very quickly, which is in order for you to decide by making this measurement if the neutrinos Majorana or Dirac, you have to be able to tell 1 from 2. That means you have to know the flux of neutrinos from the cosmic neutrino background very well, or at least at the 100% level. And it turns out that we know the average number of neutrinos very, very well, but there's some debates about what's the number of neutrinos here on Earth, as opposed to on average in the entire universe. And smart people tell me that they know the answer at the 10% level, so I'm willing to believe that, but it's also easy to screw around and change things in such a way that that number can fluctuate by a lot. So you're kind of at the mercy of knowing very precisely the number of neutrinos from the cosmic neutrino background where we are right now.
Andre, the time is up.
I know, yeah, the time is up, so I'm just going to jump to the end. So you can look at my slides very quickly, starting now. Okay, good. Good. So let me conclude very quickly. I try to give you a sense of what neutrinos were. I also try to explain that neutrino masses are very important for us because they're an indication that there are new particles, but we know very, very little about what these particles are. We have been trying to identify what nature's trying to tell us, and nature has told us that neutrino masses are very small, and we think it means something, and the theorists spend a lot of time trying to explain that. And then I try to spend some time explaining that we would like to know if the neutrinos are Majorana fermions or Dirac fermions, and then I try to give you a sense of what the question means and why it's so difficult to get an answer. So I'll stop here, thanks. Sorry about going over a little bit.
Thank you, Andre, for this really good talk. And I think that we have time for questions. So please raise your hand if, okay, Jesse.
Hi, Andre. Thank you for the really fascinating talk. I wanted to ask about these cosmic neutrino backgrounds, and I think you briefly mentioned some hope of detecting these one day, which would, of course, be an amazing discovery. Do you have a sense of what the prospects are, and how hopeful are we to detect these soon?
Yeah, so this is a very good question, and it's a problem that's been around for a very long time. People are more hopeful today than they were, let's say, 10 years ago, and the idea really is to look at this neutrino capture process. So you really want to have a nucleus that captures a neutrino and turns into an electron. Now, for people who've never thought about this, the trick is these neutrinos have very, very low energies. That means that if your physics process has any threshold, it becomes impossible to measure the neutrinos that way. Now, on the other hand, if your nucleus already knows how to undergo beta decay, that means that the energy cost of absorbing a neutrino is 0. You don't have any threshold at all. So you can basically absorb a neutrino with arbitrarily low energy. So that's a kind of step number 1. And step number 2 is, of course, the real challenge is that this nucleus is already undergoing beta decay. So it's producing a whole lot of electrons. So the question is, how can you tell that the electron that was produced was induced by a neutrino scattering as opposed to just an ordinary beta decay? And the reason is that the neutrinos come in with a little bit of an energy. So the neutrinos come in, they hit the nucleus, and they actually produce an electron that has an energy that's beyond the end of the spectrum for beta decay. So that means if you have a lot of beta decay nuclei, and you can measure the electron energy precisely enough that you can tell that you're producing electrons beyond the end of the beta spectrum, then you can convince yourself that these processes can go and that you're detecting this cosmic neutrino background. So again, the cross-section is not super tiny because it's a super allowed cross-section. And there is a signature for the neutrinos. So the challenge now becomes a technical challenge as to, can you get enough nuclei and can you measure these electrons that are coming out in a way that you can see the energy with enough resolution that you can tell it's not just a beta decay process. There's a project called the Ptolemy, and they've been looking at this and identifying what are all of the different components that you need in order to successfully do this measurement. And basically, it turns out to be similar in spirit to precision measurements of beta decay aimed at measuring neutrino masses, except that it's harder. So we've never seen neutrino masses in beta decay. But in principle, if we knew how to do that, then measuring the cosmic neutrino background is a harder version of doing that. But there seems to be a path to follow in order to get to a measurement of the cosmic neutrino background. For people that are old enough, there's all kinds of crazy ideas on how to measure the cosmic neutrino background. And to zeroth order, they're all wrong. So you don't have to worry about those. I hope that answers the question.
Yep, thank you.
Okay, thank you. David, you have a question. David Schmidt.
Mine's just a direct follow on to that then. So, you know, in a search for neutrino mass, you're looking for a reduction in the endpoint of the spectrum. And here you're saying there's an impart of additional energy. So you're looking for sort of a push out of the endpoint. So do we have to, you know, how do we disentangle those? And we have to measure this first, I guess, quite precisely before we can move on.
So here's a good. So here's a cartoon. So hopefully you can see this. So here's a cartoon of what the beta decay measurement is. So the idea is if you look at a beta decay spectrum, it ends. And if you zoom in at the very end of the spectrum, if the neutrino has a mass, there's a penalty that you have to pay to produce the electron, which is the neutrino energy, and that takes away a little bit from the spectrum. What things like the Catherine experiment are about, they're about not very much determining where the spectrum ends, but it's more like a shape measurement, right? They're measuring so the problem is, it would be great to determine where the spectrum ends, except that we don't know very precisely where the spectrum ends, even though we know that pretty precisely. And on top of that, there are no events at the end, so it's hard to detect zero events. So, but it's easier to measure a shape. So it's a shape measurement, and so you need to know precisely enough. And basically, the cosmic neutrino background. Let's say you have this blue spectrum. The cosmic neutrino background would give you some extra events over here where my hand is. So that means, and not too many of those events, by the way. So you have to have enough resolution, let's say, to convince yourself that there's a little gap and that the gap is of order 2 times the neutrino mass. I'm sure the real world analysis would be a much more sophisticated and intelligent version of that, but that's the spirit of the analysis. And the good news is that the rate is not super tiny, but again, in quotes, the beta background grows as quickly as your signal, because if you want to get a bigger signal, you need more. You can't get more cosmic neutrino background. That's a fixed number. So you just have to have more beta decay nuclei. So you have to live with both of those. Yeah, thanks. I hope this is slightly more clear. And you're reaching the limit of my knowledge, so.
Okay, Son, you have a question.
So you mentioned that people know the density of cosmic neutrino near the Earth with the 10% accuracy. What is that number compared to the average density in the whole universe?
That's a great question. And so I'm looking for this figure. So the average number is this number. It's about 100 neutrinos per cubic centimeter. And that's the number that you learn in undergraduate cosmology. It's a very well-known number that just assumes that the universe were in thermal equilibrium early on. and that they can be described by a temperature that we can calculate very precisely. Now, around here, you expect a little bit of an enhancement in the number of neutrinos because of gravity. So that, there's a little bit more neutrinos. And for a long time, people were excited about coming up with some new interactions to get that number to be larger. But if you just do the standard model calculation, that number is of order the same number here. I don't remember the exact number, but the enhancement is relatively small. If you are very, very picky, this is a many-body gravity kind of problem that you have to solve. And the question is, do you trust those calculations? And that's where this 10% number is coming from. And I'm sorry, I can't give you all the details, but it is a non-trivial question which different people have looked at. And it will rely on things like, do the neutrinos interact very much with the dark matter? And since we know nothing about the dark matter, we don't know if they interact a lot with the neutrinos, but that could have an effect. Or is neutrino gravity weird? And I'm sure some people have thought about that. And that will also change that number. But if you don't assume anything weird, then it is a calculation that can be done. You're asking how much do the neutrinos clump in our gravitational potential well. And the question is, how much do you trust that result? And that's this 10% that I've quoted.
But 10%, André, is uncertainty, not the effect.
Yeah, of course. Yeah, no.
And the effect is what?
It's not a big effect. It's less than order 1.
Very good. Are there any other questions? If not, let me ask, so you said that there are other ways to determine if these are Majorana, so could you just, without giving any detail, what would be the other ways?
So all the other ways are bad, but I'll mention them anyway because they're kind of fun. I'll just mention one very quickly. So the challenge with these very low energy experiments is that you don't have enough very low energy neutrinos around. And so I'll just say very quickly, one thing you can do is you don't need the low energy neutrinos. You can just produce them. So where am I? Sorry about this. So let's say that you measure this process. E gamma goes to E nu bar. The nice thing is you can have an electron at rest, and you can get a photon with any energy that you like. And if you do that, you can get a very low energy photon, and then you can have this E gamma to E nu bar at threshold. And if you do that, this is the ratio of the cross sections as a function of the photon energy for Dirac over Majorana. And you notice that this ratio can be an order of magnitude different. For a very simple process, E gamma goes to E nu bar. This is super exciting until you look at the plot on the left, and you notice that the cross section is kind of small. But again, the purpose of this is just to show you that at very low energies, Dirac and Majorana neutrinos are just totally different objects, and you would never be confused, except that the weak interactions are kind of merciless when it comes to very low energy processes. So that's one other example. The other examples that we also looked at is if you had a neutrino that was heavier, and then you started looking at things like neutrino decay, then it turns out that Majorana and Dirac fermions decay differently. Again, in also some very startling way. You can have qualitatively different kinematics for the decay that would instantaneously tell you that your neutrino is not a Majorana fermion. And that's what some of the other slides have.
Very good. Let's go to the last question by John Rosner. So.
I'm listening. I'll actually be walking my laptop before my battery runs out, but I'm listening.
Okay, I wonder if the scenario of a very heavy right-handed neutrino with a seesaw mechanism is the right one. What emphasis would you advocate for experiment?
That's a very good question. That scenario, so that's everybody's favorite scenario. And the idea is you postulate a very heavy right-handed neutrino, and you do this thing called the seesaw mechanism. So if that's the right answer, and if the right-handed neutrinos are very, very heavy, then this is a scenario where it is not easy to convince yourself by doing experiments that that's the right answer. Because what you would do in this case is you would first want to see neutrinoless double beta decay. So the one prediction that's relatively robust is that the neutrinos are Majorana fermions. So that's kind of prediction number one. And then if the right-handed neutrinos are really super heavy, the only other observable, in quotes, consequence of the right-handed neutrinos would be something like leptogenesis. That means that they could be responsible for the matter-antimatter asymmetry of the universe. Now, if that were the case, you would still have to convince yourself that that's the right answer. And that's very hard to do because you don't have enough experimental information. So you can only, so the good news is that that model could have been rendered false if the neutrino masses had been different by, say, a few orders of magnitude. So you could have said that leptogenesis is not possible. But we failed to do that. Leptogenesis is possible. Doesn't mean it's right. What people like to say is that we have other ideas for how to do baryogenesis. Carlos can tell you all about it. So once you show that Carlos's idea is wrong, and once you show that all the other testable ideas are also wrong, then the neutrino idea will look better. Still doesn't mean it's right. It just means it's not ruled out. But it is a possibility that we could be in a world where we don't really get to learn with a lot of precision exactly what the mechanism behind neutrino masses are if the new physics is super heavy.
Maybe Andre, you can say a few words about the connection with CP violation.
Yeah, I can try because there is a.
I know I put you in a hot spot. But...
You know, that it's a good question. So one argument that people like to pursue is if this leptogenesis idea is correct, there must be CP violation in the neutrino sector. So we have one number that we can measure to gauge if there is CP violation in the neutrino sector, which is CP violation in neutrino oscillations. So if we observe that, I think that will add credence to this leptogenesis idea. Now, the problem is the connection between the CP violation we can measure in neutrino oscillations and the CP violation that explains the baryon asymmetry is very, very indirect. That's easy to understand. It's basically in the leptogenesis Lagrangian, you have, let's say, 20 parameters. When you do a low energy experiment, you get to measure 3 linear combinations of these 20 parameters. So there's no way that by measuring 3 numbers, you can learn 20 parameters. So that's why you lose a lot of information when you integrate out the right-handed neutrinos. So in order to make progress, we need more hints. And of course, that relies on the experiment seeing something. I did want to say one thing very briefly, which is one subject that's gotten a lot of attention recently is people have been talking about this cosmic collider, which is very, very heavy physics in the very early universe, leaves an imprint in the primordial gravity waves and large scale structure at super ridiculously big Ks and blah, blah, blah. So it is possible to imagine a generation from now that we will have this access to very, very early universe physics that can teach us about very heavy degrees of freedom. And the right-handed neutrinos that live at 10 to the 10 GeV might eventually manifest themselves in that way. This is science fiction stuff, which I don't know anything about. Actually, Lian Tao has written a paper about this. I don't think he's here. But if he were here, he could correct me, and he could let us know how to discover that the seesaw is correct.
Okay, very good. So I don't see any other raised hand. So with that, we conclude the colloquium. We thank Andre again for this fantastic talk. Thank you, Andre.
Thanks, Andre.